Hello, welcome to my final year project on the topic Unified User and Task UUT-centered Artificial Intelligence for Metaverse Edge Computing. To start, Metaverse is an extension of the internet we currently use, where the separation between the physical and virtual world is bridged by extended reality, or what we call XR technologies. So with these XR-enabled devices such as headsets, glasses, watches, and gloves, users can project their physical presence, surrounding objects, and movements onto the virtual world through digital twinning. However, there are a few existing limitations regarding the Metaverse ecosystem services, which we will cover later. Our project aims to introduce a unified user and task UUT-centered MEC to serve as a foundation for future AI control algorithms to create a task-oriented and user-centric MEC. This will result in giving users a personalized, seamless, and highly realistic experience in the metaverse. To use this technology, there are several limitations. Firstly, the intricate interactions between physical and virtual worlds in XR and complex interactions between virtual entities will cause a high computational load and cannot power metaverse applications. Secondly, edge computing require optimization since metaverse impose a high computational load, hence requiring a robust and scalable edge computing infrastructure. Lastly, current works rely mainly on basic deep reinforcement learning architecture that can handle only simple mobile edge computing resource allocation problems. These architectures are not tailored to meet the varying computation and communication requirements of metaverse applications. To design an effective MEC system for metaverse applications, it is important to understand the underlying factors driving variation in user resource demands. Variation in user resource demands arise from differences in metaverse application and XR device hardware specifications, as well as user preferences and characteristics. Metaverse applications span across various sectors, each with different levels of computation and communication demands, as seen in this figure. For instance, safety-sensitive applications such as remote surgeries require high visual resolution and frame rate, alongside hyper-realistic and ultra-low latency tactile feedback. On the other hand, non-safety sensitive applications such as XR lectures have higher tolerance for computation and communication delays. XR device hardware specifications such as computation power, communication capabilities, and battery capacity also affect user resource demands. User preferences and characteristics must also be considered when designing a user and task-centered optimization algorithm for MEC. To meet the computation and communication demands of users, the MEC process for metaverse application must be optimized. Decision-making on whether a user's task should be offloaded, metaverse edge computing server selection, and channel access allocation are among the aspects that can be optimized. The user-centered AI-based algorithm handles specified and diverse metaverse by having multiple differentiated decision-making agents. However, the decisions made by agents at the control layer are not independent, as they are influenced by the decisions made by other decision-making agents. Therefore, a task-centered AI-based resource allocation MEC system is required to ensure that the sub-objectives of underlying MEC tasks are fulfilled alongside a global objective. To achieve this, a proposed user-centered deep reinforcement learning or DRL on the left and task-centered DRL on the right is proposed and can be combined together to build a unified user and task-centered DRL architecture. Like the user-centered DRL architecture, individual user states are combined and fed into the actor. The actor is responsible for generating actions for each task and will produce a reward for each user. The multi-head critic will then take in combined user states across different tasks and output advantage and loss values for each user task configuration to update the unified user and task actors and critics. The unified user and task-centered architecture has the potential to empower metaverse applications by prioritizing the user and task requirements. This architecture ensures that the AI-based mobile edge computing can deliver personalized experience that cater to individual users, while also taking into account the nature of the task at hand. As a result, the unified user and task-centered DRL architecture has the potential to significantly enhance the overall user experience and satisfaction. To verify the validity of the user-centered reinforcement learning framework, we used it to tackle a VR-scene computation offloading task. A user-centered RL architecture, traditional RL architecture, and an agent that performs random actions were employed to compare the performance of each algorithm. As you can see here, the user-centered RL architecture achieved a much higher task success rate when compared to the traditional RL algorithm across the training process. This emphasizes the superiority of a user-centered RL in tackling challenges with heterogeneous user requirements. Similarly, to examine the feasibility of the task-centered reinforcement learning architecture, a Metaverse digital twinning scenario was proposed in which smart vehicles are traveling along the roads, detecting traffic information to be uploaded to the MECS for the development of a Metaverse map. The results indicate that the task-centered deep reinforcement learning algorithm achieves the lowest delay and highest mean average precision map score across the training process as shown here. This shows that the task-centered DRL algorithm manages to achieve the highest object detection score at the lowest transmission latency. In conclusion, we have highlighted the importance of considering the communication and computation requirements necessary to support the wide range of Metaverse applications. The proposed unified user and task-centered AI-based mobile edge computing paradigm has the potential to improve the efficiency of resource allocation in a complex and dynamic multi-user and multitask Metaverse edge computing environment. This UUT-centered approach has the potential to improve the user experience by tailoring the edge computing services to the specific needs of each user and task. Future research can focus on understanding user expectations and preferences to further refine the proposed paradigm. Privacy concerns also needs to be addressed, and alternative forms of privacy-preserving edge computing can be explored. And this will be the end of the presentation. Thank you.